Hi, welcome to the future. This is a demo lesson on physics, and today we're going to look at the conservation of energy, which is something that you do both in O-level and A-level physics. So let's just dive right in. I'm going to read out the statement to you first, and then we'll talk about what it means and what the implications are, etc., etc. So the law of conservation of energy states that the total energy of an isolated system remains constant, and it is said to be conserved over time. Now, the very first question that probably comes to your mind is that what do we mean by an isolated system? Now, because this is a demo lesson, we're not going to go too far into the details as to what that means, but we'll just at least explain briefly what that refers to. So an isolated system is one that has no external forces acting on it. And again, we're not going to discuss in detail what external and internal forces are. For now, we're only going to say that we are referring to air resistance and friction when we use the word external forces. And what does it mean for it to be conserved over time? Is that the total energy remains the same. Now, using these new terms that we've defined, if I just reiterate the law of conservation to you, it will just mean that if a system has no air resistance or friction that it has to overcome, then its total energy will remain the same, which is pretty intuitive. If it's not losing energy to anything, then of course its total energy is going to remain the same. But there is something that can happen, is that despite the total energy remaining the same, it can transfer from one form into the other. And that's what part 2 is all about. It says it can neither be created nor destroyed. Rather, it can only be transferred from one form to another. So that's all of conservation of energy for you. To explain what that means, what do we mean by the total energy? So let's just look at that as well. By the total energy, we mean to say it is a sum of the gravitational potential energy and the kinetic energy. So again, if you want to scroll back up and see what that means, I can just show it to you. So what we're basically saying is that the sum of these two is going to remain the same, regardless of what is happening. And when is it going to remain the same? It's going to remain the same when there's no loss of energy. And similarly, you keep going. When is there going to be no loss of energy? When there's no air resistance or there's no friction. Because if you have some form of opposition or resistance, then you will be losing energy. If you look at this diagram right here, it's a very simple case to demonstrate what the conservation of energy means. So we have a ball that rolls from A all the way down to B and then to C and then goes back to A and then just keeps going back and forth between A and C as I'm showing on the screen right now. What we're going to do is we're going to add some values to this diagram and see what the conservation of energy really means, because a lot of people have memorized the law of conservation of energy, but they cannot explain what it means when we say that it cannot be created or it cannot be destroyed. And yeah, just before I move forward with that, if you cannot explain terms such as, the ones that I've just mentioned, creating energy or destroying energy, then it just means you don't know what you're talking about. Anyway, so at point A, it is some height above the ground. And all of you know that when something is at a height above the ground, so it's not at ground level, at any height above ground level, what that means is that it's going to have gravitational potential energy. Now, in a case like this, we don't know whether B is exactly on the ground or B is above the ground. What I mean to say by that is that the ground could be here, or the ground could just be at this point as well. So the question then arises is that which point or which reference level do we use as a ground level when we want to calculate the gravitational potential energy at A, B, or C? Now, for those of you who don't know what gravitational potential energy is, I'll just write it down right here. So an object possesses gravitational potential energy when it is raised through some height above the ground. Well, that's just loosely speaking. Now, coming back to the question is that which of the two, number one or number two, do we use as our reference level if we want to calculate the gravitational potential energy? Well, the answer to that is that it does not matter. It doesn't make any difference whether it's position one or position two. The reason being, what we're going to do is we're just going to say that the gravitational potential energy at B is 0. So that happens to be our reference level as well. This is the reference level. Now, the reason why we're doing that is because it's the lowest point in the diagram. Among A, B, and C, B is the lowest point. So if you just take the lowest point to be your reference level, it just simplifies everything. So because the height above the reference level at B is 0, it has no height above the ground level when it is at B. So that means the gravitational potential energy is 0. And again, why exactly is it 0? Because the equation to calculate the gravitational potential energy is mgh. So when h is 0, it doesn't matter what the mass of the object is, m times g times 0 is always going to give you 0. Now, at position A, the gravitational potential energy is going to be at its maximum. Similarly, at C, the gravitational potential energy is going to be at its maximum as well. What about the kinetic energy? Well, it started off right here at position A, and then it starts to go down all the way like this, and then it starts to go up. So when it's falling from A to B, it's losing height. So that means the gravitational potential energy is decreasing. Now, because the gravitational potential energy is decreasing, some form of energy must be increasing. And again, going back to our statement before, right here, we said it can be transformed or transferred from one form to another. And that is exactly what is happening here. When it goes from A all the way down to B, what's happening is that the height above the reference level keeps decreasing. So that means the gravitational potential energy is decreasing. Now, when the ball reaches B, the height above the reference level is exactly 0. So that means the gravitational potential energy is also 0. Now, the question is, where has all that gravitational potential energy gone? It has gone into the kinetic energy of the object, which is the ball in this case. And just to remind you, the kinetic energy is the energy that an object possesses because of its speed or because of its motion. So what that means is that from A to B, all the gravitational potential energy is going to be lost, and it's going to gain kinetic energy all the way. So the kinetic energy at B is at its maximum. So that's basically the entire scenario. At A, you have maximum potential energy. Why? Because the height above the reference level is maximum at that point. At B, potential energy is 0 because the height is 0, but then the kinetic energy is maximum. What that means is that at B, the ball has its highest speed. And then, so you see from A to B, ball gains speed but loses height. From B to C, the reverse is going to happen. It's going to lose speed but because of the speed that it's giving up, it tends to gain height. It goes up all the way to C, and if you realize, A and C are at the same vertical level. Now that is directly related to the conservation of energy. Okay, so we'll actually just put that thought on hold for a bit as to why it cannot go up to C dash, because I wanted to add something else here which just slipped my mind. And that is that from A to B, the gravitational potential energy goes down, but kinetic energy goes up. And then from B to C, the reverse will happen. Kinetic energy falls and gravitational potential energy increases. So that sums up the entire scenario as to what's happening from A to B to C, and then from C back to B, back to A. The whole thing will just keep repeating. Now, coming back to why cannot go up to C dash, it'll make it a lot easier if we can pick some numbers, and I'm probably going to get rid of all of this because it's getting a little too messy. Okay, so that's it. Let's say the gravitational potential energy at A is 200 joules. Then at B, the gravitational potential energy is 0. So hopefully you can calculate what the kinetic energy is going to be. And if we're having trouble doing that, let me take you back again and remind you what it means for the total energy to be conserved. It means that total energy remains the same. And we define this as well, that the sum of the potential and kinetic energies has to be the same. So again, now let's come back to the diagram again. At A, we've just released the ball. So when it's stationary, before it begins to move, it obviously had no speed. So that when it has no speed, that means it has no kinetic energy either. So it means at A, it has 200 joules of potential energy and 0 kinetic energy. And if you look at the sum right here, the sum is 200. And we said that energy is going to be conserved, which means that the sum should always remain 200. Now, because we know that at B, the gravitational potential energy is 0, then naturally we know that all of it is in the form of kinetic energy, which is also 200. If you look at the sum once again, it comes out to be 200. Now, if you look at C, it's the same thing as A. The gravitational potential energy is going to be 200, kinetic energy is going to be 0. And the sum again comes out to be 200. You see, now this is a very clear scenario as to what it means for the energy to be conserved. Let's revisit quickly. At A, gravitational potential is 200, kinetic is 0, so sum is 200. At B, the potential energy is 0, but the kinetic energy is now 200, but the sum is again 200. If we go all the way up to C, then the potential energy is once again 200 and kinetic energy is 0. The sum still remains at 200. Now, what is this telling you? How is this related to the conservation of energy? You see, no energy has been created or destroyed, because had some energy been created, the sum would have exceeded 200, and that clearly is not happening. Similarly, if some energy had been destroyed, then the sum would have been less than 200, and that is not the case either. And there is a very important underlying assumption as to why that is not happening. And again, I'll take you back to the statement that we wrote down. We said it has to be an isolated system, and we said there are going to be no external forces acting on it, which means that we're neglecting air resistance and friction. Because obviously, if friction were present in this scenario, then the sum at point C right here would not have been 200. It would have been something less. But again, let's not go too far into the details, and let's just stick to the basics for now. I feel it's already getting a little more detailed than what I had planned. Okay, so now hopefully you understand what the entire scenario is. It goes from A to B, it gains speed, loses height, goes from B to C, loses speed, but then gains height, and then the same thing will keep happening again and again as it goes between A and C. Now, all of this at times gets a little fuzzy and it's hard to understand what's going on. And this is where, a nice simulation comes into play. I've been asking you guys to watch the simulations since, I don't know, 6 months, but you don't do it. So, I'll just do it for you. And hopefully you can take out the time to watch it for a couple of minutes, because it'll do wonders in terms of explaining to you what the conservation of energy really means. And again, I'm going to drift a little bit over here. To become good at physics, you have to develop intuition about the subject, meaning that if you're given a scenario, you're given a situation, you must be able to go back to the fundamentals of what you've learned and think that, okay, what is it that's going to happen next? And again, you don't have to predict it with a certainty of 100%, but at least you should have a good basic idea of what's going to happen. And you must have good, a good grip on math in order to be good at physics. Okay, so I'm just going to play this first at normal speed, and I want you to see what's happening. This is a really nice simulation. So the person, let's go over here. Okay, I let go of the person at the top point, and he keeps, so you see what is happening. Now, what I want you to do is, I don't have the option of pointing out things right here, but if you look at the bars that are shown on the left, you see kinetic energy goes up, then goes down. When the green bar goes down, the blue one goes up. When the green one goes up, the blue one goes down. Why is it doing that? Now, let me take it to slow motion. And I will pause it right here. So at this point, if you look at the blue bar, it's showing you the potential energy. It is equal to the total energy. As we saw in the diagram, if you come back to this, gravitational potential energy is 200. The total is also 200. That's exactly what this is showing you right here. Now, if we play, then as the person moves down towards the lowest point, the potential energy is going to go down, meaning the blue bar is going to become shorter, and the green bar is going to go up because it is gaining kinetic energy. And there you go. That's what happens. So it's just going to oscillate back and forth. Now, another thing that we talked about right here, at the lowest point, you can see the blue bar for the potential energy is exactly 0, but the green bar is now equal to the other one that's shown for the total energy. What that means is that all the energy at this point is in the form of kinetic energy. So obviously, at this point, it's going to be moving at its fastest speed. And we already talked about that as well.
Okay, so now we've shown that at the lowest point, the skater has its highest speed, and at the highest points, it has the most amount of gravitational potential energy. Now, what we're going to do is add a pie chart to this as well, so that you can look at the transition, just different types of visual representations of the values. Now, this is, again, I want you to observe what's going to happen is if we release the person from this height and just let it go. So just look at it. The entire pie chart changes into blue at the top and then changes into green at the bottom. That again is showing what we've already talked about. The main thing, let me just get rid of the grid so that it's a better view. What you need to realize is that he keeps moving between the same 2 points again and again. So meaning that the maximum point he reaches on the right-hand side is at the same level as the maximum point that it reaches on the left-hand side. Now, why is that? Because if you look at the bar for friction, we've reduced friction to 0. And that's exactly what needs to be true. That means there is no external force acting. Now, what I'm going to do is just increase friction and see what happens. Okay, there you go. Now, all of a sudden, the thermal bar has also shown up. You see, after every single swing, the thermal bar keeps on going up. and the person slows down, keeps on moving to lower and lower points at every successive swing. And now right at the end, all of it has been lost as thermal energy and there's no more motion. You see, the chapter on energy is very interesting because of this reason only, is that energy transformations are all around you at all times. Well, that's it for the simulation. I think there's nothing else that I wanted to point towards. So let's just close that and go back to what we were doing. Okay, so we've talked about that. We've looked at the simulation, just another really simple diagram. Let me quickly run you through it. Is that at this point, it has no gravitational potential energy because it's at its lowest position. Now you see, this is exactly what it's talking about. This point level right here, this, it's hard to see, this is not really necessarily the ground, you know, the physical ground that we have around us. But since it's the lowest level, we will say that this is our reference level, therefore the height is 0. And so the gravitational potential energy there is also 0. Now, when it goes to this point, you can see it has the maximum height above the reference level, maximum height. So therefore it has the maximum gravitational potential energy as well. Then as it starts to fall down, so at this position, it has lost some height, right? So that means the gravitational potential energy as compared to the maximum point, the gravitational potential energy here has gone down, but kinetic energy has gone up. Then at the lowest position right here, kinetic energy is at its maximum. So just the same story as the one that we already discussed. So just to finish, we'll look at a couple of questions. These are some questions that have been taken from A-level past papers, but somebody who's good with the O-level physics in terms of the chapter on work, energy, and power will also be able to do questions. All three of these questions, in fact. So it says a trolley runs from P to Q along a track. At Q, its potential energy is 50 kilojoules less than at P. And then it goes on to say that at P, the kinetic energy of the trolley is 5 kilojoules. Between P and Q, the work the trolley does against friction is 10 kilojoules. What is the kinetic energy of the trolley at Q? Now again, the trick with a question like this is that if you have the ability to break it down, to decompose it into smaller parts, it becomes a lot easier. I can try to show you how I would do it. So at Q, it says its potential energy is 50 kilojoules less than at P. Meaning, as it goes from P to Q, 50 kilojoules of potential energy have been lost. So what that means is that 50 kilojoules of kinetic energy have been gained. So see, going back to the conservation of energy, because you've lost 50 kilojoules in the form of potential energy, that means you've gained 50 kilojoules in the form of kinetic energy. So that's one thing. The second thing is that this number right here says that at P, the kinetic energy was already at 5 kilojoules. So at right this point, kinetic energy is 5 kilojoules. Now again, how do you put both of these things together? We started off with, oh no, the battery died, so we'll just have to pause and then start again. Okay, so yeah, it's fixed. So we know that we started off with 5 kilojoules of kinetic energy at P, and that we gain 50 kilojoules of kinetic energy at Q. So then what does that put your total kinetic energy at? Total kinetic energy at Q is then 5 plus 50, which is 55 kilojoules. Well, again, that would have been true if there had been no loss of energy. But if you keep going, it says the trolley does 10 kilojoules of work against friction. What that basically means is that this is the amount of energy that has been lost. So if we had a total of 55, we lost 10 out of that, how much are we left with? We're left with 45, and that's the answer. Next question again. A car driver adjusts the pressure on a car's brakes so that the car travels at constant speed down a hill from P to Q. The magnitude of the change in the car's kinetic energy is delta EK. The magnitude of the change in its gravitational potential energy is delta EP. They're saying which statement is correct. Well, if you're good at paying attention to detail, then this should be an easy problem. Why? Just because of this fact right here. It says the car travels at constant speed. Now, let me just remind you, the kinetic energy is 1/2 mv squared. Well, you know that there are only two variables that are gonna decide how much kinetic energy the object has. It is the mass of the object and its speed. Now, obviously, the mass of the car is not changing as it goes down the hill. Now, the other thing is that if the speed is changing, then the kinetic energy will also change. But if the speed also remains the same, then the kinetic energy will also remain the same. Well, it goes at constant speed, so that means V does not change from P to Q. Well, what does that tell you about the kinetic energy? That it must remain the same. So delta EK should be equal to 0. Why? Because the symbol right here, delta, the triangle, means change in. So this whole thing right here, this thing, it means that the change in kinetic energy is 0. So when there is no change in any given quantity, of course, the change in that quantity is going to be equal to 0. So this is it. And question number 8, we'll just cut it short. You can try this yourself, and hopefully you'll get it right. So that's about it, and we're going to end right here. Thank you for watching.